Our interest here is to look at the running time of all pair shortest path algorithms. In calculating all pair shortest paths, our interest is to calculate a table of shortest paths between every vertex to every other vertex in the graph. So given S, we want to find the shortest paths between S and A, S and B, S and C, S and D, S and E, and same for shortest path between A and S, A and B, A and C, and so on. What we know is that to calculate single source shortest path, we have the Dijkstra's algorithm and the Bellman-Ford algorithm. So these are single source shortest paths algorithms. Single source, that is, given one starting vertex, they give you the shortest path between that vertex and every other vertex in the graph. So the running time of Dijkstra's algorithm is big O of v squared log v plus ve. This is assuming that the priority queue is implemented using Fibonacci heap. And similarly, the running time of the time complexity of the Bellman-Ford algorithm is big O of VE. Now, we could have a graph very sparse where the number of edges in the graph is very close to the number of vertices in the graph. And we could also have a graph which is dense, that is, the number of edges is very close to the square of the number of vertices. This is more like a complete graph. So let's see how these two algorithms' time complexity changes for a sparse graph and dense graph. So in a sparse graph, since E is almost close to V, so this becomes big O of V square log V plus V square. And now, since V square log V is bigger than V square, I can remove these terms, so the running time becomes V square log V. In the case of dense graph, we have E almost close to V square, so this becomes big O of V square log V plus V cube. And since V cube is very high compared to this one, this term goes out, so the running time becomes big O of V cube. Similarly, for the Bellman-Ford algorithm, since here in a sparse graph V is almost equals to E, so the running time becomes big O of V square. And in the case of dense graph, this becomes big O of V cube. One very easy trick to compute all pair shortest path is to simply run one of these two algorithms at every vertex of the graph. So I can run Dijkstra's algorithm with S as my starting vertex, and then A as my starting vertex, and B as my starting vertex repeatedly for each of the vertex in my graph, and then obtain all pair shortest path. So if we simply do that, say for example using Dijkstra's algorithm, then the running time of the all pair shortest path algorithm, the time complexity becomes, so this will be this run V times, so big O of V times V squared log V plus VE. Now in the case of a sparse graph, so this becomes big O of V cube log V. And in the case of a dense graph, this becomes big O of V to the power 4. Because V cube run V times becomes V to the power 4. Similarly, if we want to obtain all pair shortest path with Bellman-Ford algorithm, then the running time here becomes big O of V square E. And in the case of a sparse graph, this becomes big O of V cube. And in the case of dense graph, this becomes big O of V to the power 4th. Now obviously, so this is easy because if I have implemented Dijkstra's algorithm or Bellman-Ford algorithm, I can simply obtain all pair shortest paths in my graph by running either of them V times. The question is, can we obtain an algorithm that runs faster than this? That is, in the worst case, this running time is big O of V to the power 4th, to the power 4. So can we have an algorithm that can do better than that? So one proposed algorithm is to use a dynamic programming to solve the all pair shortest path algorithm. Now the default dynamic programming algorithm runs in big theta of V to the power 4th. So since this is big theta, whether it's a sparse graph or dense graph, the running time stays the same. So this isn't very exciting because this is same as the time that would need if we called Bellman-Ford or de Kruijstra's V times. But then with some improvements to this dynamic programming algorithm, if we improve the algorithm, this can actually run in big theta of v cube log v time, which is improvement. And since this is big theta, whether the graph is sparse or dense, that will also always be the running time. Now, however, the Floyd-Warshall algorithm further improves the time complexity, and this gives us a big theta of v cube time complexity. And since this is a big theta, whether it's a sparse graph or dense graph, the running time becomes still the same. So dynamic programming implementation is not faster than the Floyd-Warshall algorithm, but it lays out some foundations that are helpful for us to understand how Floyd-Warshall algorithm works. Now, this is a dynamic programming approach. This extends the recursive implementation of the overall algorithm and then uses greedy approach to achieve this running time of big theta v cube.